Thank you, Mr. Chairman. I'm very pleased to be able to present ongoing works and trends in modeling for nuclear safety. And my talk will be divided in three different ways. First, I will record just an insight into probabilistic safety assessment for nuclear plants, what is intended and what we want to achieve. And I will present a focus on two different ways which are very complementary with respect to these strategies of safety assessment, probabilistic safety assessment, and which aim at having also complementary ways of getting efficiency in computing and perspective. So first, as was nicely introduced, I will talk a bit about NARCIS because it's a research project which is dealing with reactor safety improvements and in which things I will present, the focus I will present are going on. So the main objectives is to get improvements related to gaps that were observed in recent nuclear accidents, and with respect to what is usually done in safety, which is the probabilistic safety assessment. It's a specific methodology which is, I will define just hereafter, and related to external events. So usually the practice is more single hazard oriented, and so the innovation here is to try to find a way to combine external events, natural events or not natural, but here I focus only on natural events, and to address, of course, things which are more low probability but high consequences with respect to the environment and people. And the objective is to improve this practice based on other ongoing research or past research, recent research, and focusing on four main hazards, natural hazards, which can be, of course, combined or cascade. We are focusing in projects on earthquakes, tsunamis, flooding, whatever flooding, can be river or it can be coastal flooding, and also extreme meteorological hazards, such as high winds, storms, and drought or heavy winds or heavy rains. So the framework of all these researches are about what we call extended PSA. PSA is the name for probabilistic safety assessment, where we try to calculate the risk induced by main sources of radioactivity related to the plant, and also to account of all possible plant operating states and for each source of possible risk, and also trying to simulate relevant accident initiating events, which can be internal or external or combined, and which can affect the site or many sites. So this is the usual way of doing. And in the project we adopt a threefold methodology, which is more related to theoretical improvements with respect to all the possible aspects of this combined multi-hazard assessment. So it can be with respect to the hazard itself, how we can improve the knowledge about them and uncertainties, how we can get more robust fragility and vulnerability models, and how we can model multi-risk through different types of framework, for instance, Bayesian. And what I will show is more related to what we try to do with the applicability and robustness of the proposed improvements with respect to safety assessment. And so we try to test on virtual plants, nuclear plants, so we are focusing mainly on pressurized water reactors, but so we have designed virtual cases in which we try to see how we can improve the safety, and also we have a demonstration level on the real site. So for the first focus, I'm talking on what I said. It's a complementary or two-way parallel development research. One is more on techniques and what can improve the computational efficiencies, but not necessarily only through brute force and HPC. And the other one is more HPC-like. So the first one is related to what we call model reduction techniques and parameterization of what we want to do, that is to produce virtual charts. And this is the team in my lab and partners that are working on this subject. So what are the motivations for virtual charts? As I said, we want to find different ways of reaching computational efficiency. So what we want is to have a sort of a parameterization technique in order to solve time-dependent nonlinear problems, which is really the case when we are talking of natural hazards and power plants. And we want to have, of course, efficiency in terms of reduced time cost. We want to be able to deal with a family of problems which can be close and which can be a sort of a typology, and like in order to gain time with the design or with the data use. And also we want to be able to work offline or online. Offline meaning that we want to get the necessary inputs or pre-computed states in case, for instance, of a accident or incident with respect to a plan. But we can also work online. So we want, for instance, use virtual charts as a decision-making tool when there's something ongoing, in order to be able to act as fast as possible. So the reduction techniques are very valuable in this sense, and very useful for virtual charts production with quite reduced cost. So our objective here is to be able to pre-compute different states of a plant or a site, nuclear site, for instance, with respect to different scenarios, so seismic scenarios, for instance, and to be included easily in a probabilistic assessment way. So, as you know, there are huge uncertainties and variabilities of this, of every step, I would say, in the process. So the input, of course, with the respect of the scenarios, but also with respect to the structural behaviors or equipment behaviors. So there's need also for probabilistic assessment to be able to produce numerous simulations, which for many aspects are still not very efficient in the computational way. What I would say is for nuclear computations and simulations, parts of them are still not really parallel, so many weeks are needed to do a full simulation of even a damaging structure, and with all the uncertainties to account for. So our purpose was to of course, diminish this time. So the proposed approach we use for reduction is what we call latent PGD. So it's a large time increment with proper generalized decomposition method, which is a non-incremental method, which is well dedicated to nonlinear solving. And which is used to parameterize resolution. So the so-called model reduction techniques, even with a very large number of parameters and a large number of loading cycles. But however, there are still scientific bottlenecks with this method. For instance, if we deal with static loading, it's not a problem, but dynamic loading like earthquakes is still a problem. It's never been applied in this domain. And loading for large number of cycles are usually described in very simple way, especially for dynamic loading, which is not coherent with the seismic loading with respect, for instance, to the number of frequencies we have to deal with, and also with the seismic input signals, which can be very different. So the ingredients of this method is to split difficulties. We split in two different spaces. One space is related to the behavior, constitutive modeling of things we want to model, and the other is a sort of an admissibility space where we have to verify the state equations like kinetic or equilibrium equations over the whole time space. So the principle is to have an iterative resolution by turning two steps and having search directions, and the main point is to have a global time-space solving at once, and to have different back and forth with respect to constitutive modeling. So this is the case, for instance, if you have a nonlinear modeling for constitutive materials, then you will have to have a local step with respect to the initial guess, which was the global time-space guess, and you will iterate between this local step to solve constitutive relationship on all space integration points and at each time step, and to come back then to the global step also on the whole space and the whole time domain at once. So it's a bit tricky, but it's really a way to reduce and parameterize the model. Then when you are iterating, you seek for an approximate of the global solution, which is a time-space form, and which is decomposed with what we call the PGD, so proper generalized decomposition modes, which can be a certain number, depends on the accuracy you want to get for the global solution, and the quantity you want to have as solutions depends on your problem, of course. So, for instance, when we are talking of structural behavior, we seek for stresses or strain rates, and each are decomposed with respect to this basis, and the number of modes will govern the time efficiency of your computations, also accuracy. And then what you do is having a sort of a fixed point algorithm to get to the convergence, to the converged solution with respect to iterating between space and time for the global step. So this is a quick overview of this methodology, of course. There are many papers on that, especially by the team doing this work. And what is really interesting for such a method is that it can be used to solve parameterized problems quite easily, because once you get to a converged solution for one state, for instance, for one type of constitutive material behavior, it's not very demanding in terms of computations to get, for instance, another type of behavior, because you start from the already previously converged solution to go to the next converged solution. So it's really fast in terms of computation, so you're not obliged to do all over again. So it's really fitted for parameterized programs. So if I sum up a bit with respect to standard step-by-step methods, if you were using, for instance, incremental like a Newton-Raphson scheme, you would do a time loop, and convergence in each step is needed to get to the solution. And with this method, it's also it's non-incremental because we do it globally, but it's sort of a Newton-Raphson process in each convergence loop. So it's a bit inverted with respect to the looping. So just a simple example, which was done really simply with a few doves. So it was 142,000 doves. So it's very small with respect to what we've seen here. But as I said, it's another way also to try to get efficiency, which can be then used for more demanding problems. So with this simple 3D nonlinear parameterized problem, which was in viscoelasticity with simple quasi-static loading, we were able to show that for comparison with the standard computation, we have a 30% gain already on the simulation run. So it's already interesting in itself without any parallel implementation. And as I said, it's very useful for parameterized program because, for instance, here it's an example of what we can do with virtual charts, meaning that we can have different parameters variation, so different sets of parameters with different types of variation. So you can have a lot of sets of parameters, and this process is easily parallel if we want to implement it in parallel. And it's also very efficient with respect to the time reduction, because, for instance, this case, which was only on 12 cores, took only a few hours with respect to many days if we were not using this reduction technique. So it's really interesting to use as a concept. The other type, of course, is HPC, because many people here are more dealing with HPC, I assume. So what we are doing now with this respect is, of course, to achieve full-firm finite element best estimate, what we call best estimate high fidelity 3D modeling. And for the same purpose of probabilistic safety assessment of nuclear sites. Here I will show the developments which are related also to earthquakes, but it's also possible to use, of course, with different other aspects, like flooding or whatever. And so the purpose is to be able to model everything with respect to the site, including multiphysics, I would say, and interactions, so between all components of the problem, and having very detailed material behaviors going to damage, because if we want to talk of accidents, it's important to talk of damage also, and also to include uncertainty. So we want to have a full parallel perspective for computing, and also for all the chain, and to work on exascale or multi-core computing architectures. But we are also trying to have another way, which is to improve the everyday laptop, which are already a few cores, but to improve the practice and to use these methods. So the ongoing developments are related to solvers mainly. So we are working a lot on different types of solvers, which are based on domain decomposition, and which are related to damage mechanics and dynamics. We are also working on the preconditioning with different types of preconditioning to improve the performance. And we are proposing we have implemented a vectorial finite element approach, which is quite useful for also efficiency with respect to what we are seeking. And we want a fully parallel process from the right beginning of the problem to the post-processing of the problem. So what we have adopted for the moment, at least, is to go on a hybrid solver strategy because of the pros we can find in such a solver with respect to the other types of solving strategies. So I won't detail that. So about preconditioning, of course, we want to have a faster solution and decrease the number of iterations, because also we have very ill-conditioned problems usually with respect to what we are simulating, and also strongly coupled problems. We want to increase the efficiency of our algorithm, so we have used preconditioning strategy, which is based on the Klein subspace method, and with a multi-level preconditioning grid, multi-grid preconditioning. So what we are using is the alternative way of using multi-grid preconditioning, which is the algebraic multi-grid preconditioning, because it's quite well suited when you have unstructured meshing, and you're not obliged to have additional meshes all the time to refine. So we are working on operators, and the cons, however, is the difficulty to implement such alternate preconditioning method, because we have to tune each time we have to use it. We have to tune the threshold parameter, for instance, which is the Coulson rate. And however, the pros are we have reduced computing cost and very high scalability. So the applications so far have been on damage mechanics and earthquake engineering. And for instance, this is an example of a 3D brittle cracking in a randomly perforated medium, which was done in a static. It was not dynamic in this case. And we were using what we call a hybrid phase field formulation, so a specific formulation for damage mechanics. And what we have implemented is a in-house monolithic vector FEM, as I said, which is quite efficient for solving with the crack propagation problem, as we need extremely refined meshing and unstructured meshing. We have used this parallel strategy to be able to compute the solution. So the thing is that we have a pre-cracking, and the whole crack is propagating along the medium. And what we see, for instance, on these figures, is that we get a really good scaling, for instance, for this vector FEM solving. It's almost linear scaling with, so it was a reduced, however, core, so the more and more cores are ongoing to see the real improvement. And the other types of applications that are more related to what I've said is probabilistic safety of nuclear sites. So we have done, I'm sorry, I cannot say where, but we have done computations for a real site in France, and using the in-house vectorial FEM dynamic solver we have implemented with the basin and all the strategy related to MPI, based domain decomposition methods, and what we have obtained here again, it was that we obtained monolithic residual drop of algebraic multigrid preconditioning, which is almost theoretical, and we have also quasi-linear scaling, even with more than 12,000 cores. So we are still going to have more cores. So it's really promising for the rest of our applications. And what we want to do is to be able to test, of course, nonlinear dynamic solver strategies we are developing, but to test them on different supercomputers and architectures, because we know that it's interesting to see whether these developments algorithms are interesting for different architectures. At CA we have already nice architectures, but we have also an ongoing collaboration with RIKEN, so we hope that maybe we could test one day these solvers on R-CCS supercomputer. And in order to test for real sites, we have data, of course. So we want to increase the domain size to include all the, for instance, seismic source in our case, and to be able to increase the number of seismic scenarios for assessment. And also, as I have not mentioned yet, we are going towards what we call full digital twins for nuclear plants. So it's a big project in France, at least, maybe elsewhere. So we want to be able to go to this and to be able also to do what we call hybrid testing. So hybrid testing is real-time assimilation between physical data and simulations. So all these developments are going in this way. And this will be mostly possible if we can combine with modeling reduction techniques as I've presented. Because, as I said, it's nice to use because of the way we parameterize everything. So we can parameterize, for instance, the loading and seismic scenarios, but we can parameterize the structure, we can parameterize everything. So we are developing some simulations strategy with respect to this combined methodology with parameterized inputs, using also big data strategies for clustering of data, and combining with the damage or consequence indicators with respect to the plants, and to produce these virtual charts, which will be useful for practical practitioners. And these methods will permit to have a real probabilistic assessment, as I said, changing parameters or scenarios are already in the methodology, so it's a way to do it. Thank you for attention.
Thank you, and very nice talk.